Hey everyone, it's the fabulous duo here. My name is Yo Ziqing.
Hi everyone, my name is Lo Shui-Qi.
Have you ever wondered how a 3-floor elevator door works? Well, it works by a combinational logic system. In this video, we'll be finding out the details, so stay with us. We'll first list out the given inputs from a combinational logic circuit. The inputs are M for the elevator moving, A for it to be at floor 1, B for it to be at floor 2, C for it to be at floor 3, and for the output we denote as O, which is to open its doors. Our first condition is that we might not want the elevator to open its doors while it's moving. Hence, all outputs when M equals to 1 cannot be 1, which is when M equals to 1, O does not equals to 1. Next, if the elevator is not moving, the elevator will also not be at more than one floor at a time. So, given this condition, we know that if the inputs show that the elevator is more than one floor, the output will be a don't care state. Hence, when M equals to 0, more than one floor input shows 1, O equals to a cross. Lastly, if the elevator is not moving too, but it is not properly aligned with any floor, the door should not open. Hence, when M equals to 0, A or B or C does not equals to 1, O equals to 0.
Given that the variables are defined and the desired case are mentioned, so our truth table will be shown next.
From the truth table, we see that when input M equals to 1, all outputs are either 0 or don't care state. On the other hand, when input M equals to 0 and either input A or input B or input C is equal to 1, then the output yields 1. This means that the truth table satisfies our condition. This is the schematic logic circuit drawn using MultiSim.
This is our prototype. It has a breadboard, 4 100 ohm resistor, 1 150 ohm resistor, 4 switches, a 7404 NOT gate IC, a 7408 AND gate IC, a 7432 OR gate IC, a power source, and a yellow LED. The switches each represents their own inputs respectively. To test our prototype, we will feed the circuit with the input based on the truth table to see if it works exactly as desired. We shall divide into two parts. First, with input M equals to 0. Then with input M equals to 1. First, when input M is equal to 0 while the other inputs are 0, okay, we turn on our power source. The LED does not light up. Hence, the output is 0. Our truth table is correct. Now, while input M equals to 0, either input A, B or C equals to 1. A equal to 1, the LED lights up. B equal to 1, the LED lights up, and C equals to 1, the LED lights up. This proves our truth table is correct. On the other hand, while input M is always equals to 1, okay, when input M is always equals to 1, while the other inputs are equals to 0, the LED does not light up. Our truth table is correct. Also, when M equal to 1, input A equal to 1, the LED does not light up. Okay, when M equal to 1, B equal to 1, the LED does not light up. When M equal to 1, C equal to 1, the LED also does not light up. This proves our truth table is correct.
If one of our input pins is left unconnected, meaning no signal applied to it at all, when this happens, the input pin floats. It floats between high 1 and low 0. When this happens, the output will produce something that we don't want. The output now becomes unreliable.
Based on our prototype, if input O is not connected, we take off the resistor. We find that the LED doesn't light up no matter what state the other inputs are at. Also, if one of the inputs A, B or C is not connected, we take off resistor from input A, the LED doesn't light up no matter what state the other inputs at.
In the process of building the prototype, some problems were encountered. We burnt a few LEDs while connecting the circuit step by step. This is because we lack proper equipment to test the voltage in the circuit. Hence, an equipment such as a multimeter shall be used to test the voltage in the circuit, to make sure the components in the circuit do not blow off.